Hello, everyone. Welcome to my Data Camp tutorial series. I'm Professor Adam Kroom, and today we will focus on Intermediate R, Chapter 5. And Chapter 5 focuses on utilities. Mathematical utilities. Have another look at some useful math functions that are features. Abs, calculate the absolute value. Sum, calculate the sum of all the values in a data structure. Mean, calculate the arithmetic mean. Round, round the values to 0 decimal places by default. Try out question mark round in the console for variations of round and ways to change the number of digits to round to. As a data scientist in training, you've estimated a regression model on the sales data for the past 6 months. After evaluating your model, you see that the training error of your model is quite regular, showing both positive and negative values. The error values are already defined in the workspace on the right. Instructions. Calculate the sum of the absolute rounded values of the training errors. You can work in parts or with a single one-liner. There is no need to store the result in a variable, just have R print it. Okay, so print sum abs round errors and make sure our syntax is good. So we got 1, 2, 3, 4 open parentheses, 1, 2, 3, 4 close parentheses. Submit our answer. Great, head over to the next exercise. And this exercise is find the error. We went ahead and included some code on the right, but there's still an error. Can you trace it and fix it? In times of despair, help with functions such as sum and rev are a single command away. Simply use question mark sum and question mark rev in the console. Instructions. Fix the error by including code on the last line. Remember, you want to call mean only once. Okay, so we want to fix the error here. We want to call mean only once. So and we want to include code to fix this. So let's try this. Submit answer. Nice work. If you check out the documentation of mean, you'll see that only the first argument, x, should be a vector. If you also specify a second argument, R will match the arguments by position and expect a specification of the trim argument. Therefore, merging the two vectors is a must. All right, next is data utilities. R features a bunch of functions to juggle around with data structures. SEQ generates sequences by specifying the from, to, and by arguments. REP replicate elements of vectors and lists. Sort a vector in ascending order, works on numerics, but also on character strings and logicals. REV reverse the elements in a data structure for which reversal is defined. STR, display the structure of any R object. Append, merge vectors or lists. This right here is dot asterisk, right, parentheses, check for the class of an R object. This right here, as dot asterisk parentheses, convert an R object from one class to another. Unlist, flatten lists to produce a vector. Remember the social media profile views data? Your LinkedIn and Facebook view counts for the last 7 days are already defined as lists on the right. Instructions. Convert both LinkedIn and Facebook lists to a vector and store them as LinkedIn vector and Facebook vector respectively. Next, append Facebook vector to LinkedIn vector. Save the result as social vector. Finally, sort social vector from high to low. So let's look on the right and think for a moment what we have to do. So we want to assign something to LinkedIn vector, so, or li underscore VEC. And that is going to be this, unlist LinkedIn. And then similarly for FB underscore VEC, unlist Facebook. And then next, what we want to do, we want to assign something to social underscore VEC. And what we want to assign is append li vector fb vec and after length li. Boom. Make sure our syntax is good. All right. So far, so good. Last but not least, we want to sort. And it says sort from high to low. So let's go sort social. We want to sort this by decreasing. So set decreasing to true. And let's submit an answer. Wonderful. These instructions required you to solve this challenge in a step-by-step approach. If you're comfortable with the functions, you can combine some of these steps into powerful one-liners. All right, next, let's find the error. Just as before, let's switch roles. It's up to you to see what unforgivable mistakes we've made. Go fix them. All right. So correct the expression. This is the instructions. Correct the expression. Make sure that your fix still uses the functions REP and SEQ. So it wants us to fix this while still using these. So let's try. Submit the answer. Sweet. Wonderful. Debugging code is also a big part of the daily routine of a data scientist. And you seem to be great at it. Let's continue. Next exercise is beat Goss using R. There is a popular story about young Goss. As a pupil, he had a lazy teacher who wanted to keep the classroom busy by having them add up the numbers 1 to 100. Goss came up with an answer almost instantaneously, 50-50. On the spot, he had developed a formula for calculating the sum of an arithmetic series. There are more general formulas for calculating the sum of an arithmetic series with different starting values and increments. Instead of deriving such a formula, why not use R to calculate the sum of a sequence? Instructions. Using the function SEQ, create a sequence that ranges from 1 to 500 in increments of 3. Assign the resulting vector to a variable SEQ1. Again, with the function SEQ, create a sequence that ranges from 1200 to 900 in increments of -7. Assign it to a variable SEQ2. Finally, calculate the total sum of the sequences either by using the sum function twice and adding the two results, or by first concatenating the sequences and then using the sum function once. Print the result to the console. So the first thing we're going to do on the right side is create a sequence and assign the resulting vector to variable SEQ1. So this is a variable SEQ1. We're going to assign something to that. And what we're going to assign is sequence 1 to 500 by 3. And we're going to assign something else to variable SEQ2. And what we're going to assign is a sequence 1200 to 900 by -7. And then we're going to calculate the total sum. Total sum, that will be the sum of SEQ1 plus sum SEQ2 and then we need to print this. So we'll just type it again, submit answer. Oh, okay, I must have made a slight error somewhere. So sum sequence 1 plus sum sequence 2. Oh, forgot the equal sign. So let's try it again. All right, great. Nice. Head over to the next video and learn more about regular expressions. We'll go ahead and skip the video. So we can work on the next exercise. In their most basic form, regular expressions can be used to see whether a pattern exists inside a character string or a vector of character strings. For this purpose, you can use grepl, which returns true when a pattern is found in the corresponding character string. Grep, which returns a vector of indices of the character strings that contains the pattern. Both functions need a pattern and an x argument, where pattern is the regular expression you want to match for, and the x argument is the character vector from which matches should be sought. In this and the following exercises, you will be querying and manipulating a character vector of email addresses. The vector emails has already been defined in the editor on the right, so you can begin with the instructions straight away. Instructions. Use grepl to generate a vector of logicals that indicates whether these email addresses contain edu. Print the result to the output. Do the same thing with grep, but this time save the resulting indexes in a variable hits. Finally, use the variable hits to select from the emails vector only the emails that contain edu. All right, so first we'll use grepl to match for edu. grepl pattern edu x equals emails. Next, we'll use grep to match for edu, save result to hits. So we're going to save a result to hits. We'll use grep pattern equals edu x equals emails. And subset emails using hits. So emails, hits, and submit. Bellissimo. You can probably guess what we're trying to achieve here. Select all the emails that end with edu. However, the strings education@world.gov and invalid.edu were also matched. Let's see in the next exercise what you can do to improve our pattern and remove these false positives. You can use the caret and the $sign to match the content located in the start and end of a string respectively. This could take us one step closer to a correct pattern for matching only the .edu email addresses from our list of emails. But there's more that can be added to make the pattern more robust. The @ sign, because a valid email must contain an @ sign. Asterisk, which matches any character 0 or more times. Both the dot and the asterisk are meta characters. You can use them to match any character between the @ sign and the .edu portion of an email address. We can use this to match the .edu part of the email at the end of the string. This part escapes the dot. It tells R that you want to use the dot as an actual character. Instructions. Use grepl with the more advanced regular expression to return a logical vector. Simply print the result. Do a similar thing with grep to create a vector of indices. Store the result in the variable hits. Use emails hits again to subset the emails vector. All right, so looking over here on the right side, use grepl to match for .edu addresses more robustly. We're going to use this pattern equals at dot asterisk dot edu x equals emails. Use grep to match for .edu addresses more robustly, save result to hits. So saving the result to hits, we're going to use grep and pattern equals at dot asterisk dot edu x equals emails. And then we will subset emails using hits. So emails using hits. Submit answer. Great. A careful construction of our regular expression leads to more meaningful matches. However, even our robust email selector will often match some incorrect email addresses. For instance, kiara@fakemail.edu. Let's not worry about this too much and continue with sub and gsub to actually edit the email addresses. While grep and grepl were used to simply check whether a regular expression could be matched with a character vector, sub and gsub take it one step further. You can specify a replacement argument. If inside the character vector x, the regular expression pattern is found, the matching elements will be replaced with replacement. Sub only replaces the first match, whereas gsub replaces all matches. Suppose that emails vector you've been working with is an excerpt of DataCamp's email database. Why not offer the owners of the .edu email addresses a new email address on the datacamp.edu domain? This could be quite a powerful marketing stunt. Online education is taking over traditional learning institutions. Convert your email and be part of the new generation. Instructions. With the advanced regular expression, use sub to replace the match with @datacamp.edu. Since there will only be one match per character string, gsub is not necessary here. Inspect the resulting output. All right, so we're going to use sub to convert the email domains to datacamp.edu. So we're going to use sub pattern at replace that with datacamp.edu x equals emails. And submit answer. Awesome. Notice how only the valid .edu addresses are changed while the other emails remain unchanged. To get a taste of other things you can accomplish with regex, head over to the next exercise. All right. Regular expressions are a typical concept that you'll learn by doing and by seeing other examples. Before you rack your brains over the regular expression in this exercise, have a look at the new things that will be used. Dot asterisk, a usual suspect. It can be read as any character that is matched 0 or more times. This, match a space. The S is normally a character. Escaping it makes it a meta character. This, match the numbers 0 to 9 at least once. This, the parentheses are used to make parts of the matching string available to define the replacement. This part right here in the replacement argument of sub gets set to the string that is captured by the regular expression. And look at this chunk of code. What does this code chunk return? Awards is already defined in the workspace, so you can start playing in the console straight away. And here are some possible answers. A vector of integers containing 1, 24, 2, 3, 2, 1. The vector awards gets returned as there isn't a single element in awards that matches the regular expression. A vector of character strings contains 1, 24, 2, 3, 2, 1. A vector of character strings containing 1, 1 Oscar, 24, 2, 3, 2, 1. Let's go with this one. Great. Can you explain why all of this happened? This selects the entire number that comes before the word nomination in the string, and the entire match gets replaced by this number because that reference to the content inside the parentheses. The next video will get you up to speed with times and dates in R. So we'll go ahead and skip this video and continue with the exercises. Right here, right now. In R, dates are represented by date objects, while times are represented by POSIXCT objects. Under the hood, however, these dates and times are simple numerical values. Date objects store the number of days since the 1st of January 1970. These objects, on the other hand, store the number of seconds since the 1st of January in 1970. The 1st of January 1970 is the common origin for representing times and dates in a wide range of programming languages. There is no particular reason for this. It is a simple convention. Of course, it's also possible to create dates and times before 1970. The corresponding numerical values are simply negative in this case. Instructions. Ask R for the current date and store the result in a variable today. To see what today looks like under the hood, call unclass on it. Ask R for the current time and store the result in a variable now. To see the numerical value that corresponds to now, call unclass on it. All right. So get the current date today. Okay, so we'll make this a variable today, and go that. See what today looks like under the hood. So we'll unclass it. Get the current time. Assign that to a variable now. So now and sys time. And now see what now looks like under the hood. So to do that, we're going to unclass now and submit answer. Great. Using R to get the current date and time is nice, but you should also know how to create dates and times from character strings. Find out how in the next exercises. All right, so this exercise is create and format dates. To create a date object from a simple character string in R, you can use the as.date function. The character string has to obey a format that can be defined using a set of symbols. And these are our symbols: 4-digit year, 2-digit year, 2-digit month, 2-digit day of the month, weekday, abbreviated weekday, month, abbreviated month. The following R commands will all create the same date object for the 13th day in January of 1982. Notice that the first line here did not need a format argument because by default, R matches your character string to the formats here or here. In addition to creating dates, you can also convert dates to character strings that use a different date notation. For this, you use the format function. Try the following lines of code. Instructions. In the editor on the right, 3 character strings representing dates have been created. Convert them to dates using as.date and assign them to date 1, date 2, and date 3 respectively. The code for date 1 is already included. Next, extract useful information from the dates as character strings using format. From the first date, select the weekday. From the second date, select the day of the month. From the third date, you should select the abbreviated month and the 4-digit year separated by a space. Okay. So we are going to convert the strings to dates and assign them to date 1, date 2, and date 3. So date 1 is already provided for us. So next, date 2 is as.date STR2. And date 3 is as.date STR3 format equals, and this is going to be percent day percent and percent y. And what's next? Convert dates to formatted strings. So format date 1, okay, and then format date 2 is percent lowercase d, and then format date 3, comma, and this one is percent lowercase b, percent uppercase y. Let's try this. You're a date magician. You can use these objects, time objects in R, in a similar fashion. Give it a try in the next exercise. All right, so create and format times. Similar to working with dates, you can also use as POSIX CT to convert from a character string to a time object as format to convert from a time object to a character string. Again, you have a wide variety of symbols. This, hours as a decimal number. This, for hours as a decimal number, 1 through 12. This for minutes as a decimal number. This for seconds as a decimal number. This for shorthand notation for the typical format. And this AM/PM indicator. For a full list of conversion symbols, consult the STRP time documentation in the console. Question mark, STRP time. Again, as.POSIX-CT uses a default format to match character strings. In this case, it's this. In this exercise, abstraction is made of different time zones. Instructions. Convert to strings that represent timestamps, str1 and str2, to time objects called time1 and time2. Using format, create a string from time1 containing only the minutes. From time2, extract the hours and minutes as hours, minutes, and PM. Refer to the assignment text above to find the correct conversion symbols. All right, so let's look over here and think about what we have to do. So we need to convert the strings to time objects. So we have time1. All right, now we need to time2. Let's include this. And this is as.POSIX-CT str2. And now convert times to formatted strings. So we're going to go format time1 question or percentage capital M, and format time2. This one is that percent M and percent P. Let's try this. Great. Press enter to continue. Next exercise is calculations with dates. Both dates and time objects are represented by simple numerical values under the hood. This makes calculation with time and date objects very straightforward. R performs the calculations using the underlying numerical values and then converts the result back to human readable time information again. You can increment and decrement date objects or do actual calculations with them. To control your eating habits, you decide to write down the dates of the last 5 days that you ate pizza. In the workspace, these dates are defined as 5 date objects, day 1 to day 5. The code on the right also contains a vector, pizza, with these 5 date objects. Instructions. Calculate the number of days that passed between the last and the first day you ate pizza. Print the result. Use the function diff on pizza to calculate the differences between consecutive pizza days. Store the result in a new variable, day_diff. Calculate the average period between 2 consecutive pizza days. Print the result. All right, so let's go ahead and look on the right. First thing we need to do is the difference between last and first pizza day. So this is going to be day 5 minus day 1. Next, create vector pizza. So it's pizza, C, day 1, 2, 3, 4, day 5. Okay. Create differences between consecutive pizza days with day assigned to day diff. Okay. So day underscore diff, we'll assign to that the difference of pizza. And then finally, let's find the average period between 2 consecutive pizza days. So the average day diff. And let's submit an answer. Great. Head over to the next exercise. Calculations with times. Calculations using time objects are completely analogous to those using data objects. Try to experiment with this code to increase or decrease time objects. Adding or subtracting time objects is also straightforward. You're developing a website that requires users to log in and out. You want to know what is the total and average amount of time a particular user spends on your website. This user has logged in 5 times and logged out 5 times as well. These times are gathered in the vectors login and logout, which are already defined in the workspace. Instructions. Calculate the difference between the two vectors, logout and login, i.e., the time the user was online in each independent session. Store the result in the variable time online. Inspect the variable time online by printing it. Calculate the total time that the user was online, print the result. Calculate the average time the user was online and print the result. All right, so the first thing we want to do is calculate the difference between login and logout and assign this to time online. So time online is our variable, and we want to assign something to that. What we want to assign is the log out minus login. And next we want to inspect the variable time underscore online. So to inspect the variable, we're just going to look at it. Calculate the total time online. So to calculate the total time online, what we'll do is, and we want to assign it to total time online. So we'll do this. Total time sum time online. And it wants us to print it. So to print, we can just type it again or also wrap that and write print. All right, so you can also obviously do that. We'll just do that for right now. And then the last thing is calculate the average time online. So we'll go like mean time online, and this will be the mean of time online. And then it wants us to print the result, so we'll go ahead and just write that again. And let's submit the answer. Great, time to tackle the final exercise of this course. Awesome. So time is of the essence. The dates when a season begins and ends can vary depending on who you ask. People in Australia will tell you that spring starts on September 1st. The Irish people in the Northern Hemisphere will swear that spring starts on February 1st with the celebration of St. Brigid's Day. Then there's also the difference between astronomical and meteorological seasons. While astronomers are used to equinoxes and solstices, meteorologists divide the year into four fixed seasons that are each 3 months long. A vector, astro, which contains character strings representing the dates on which the four astronomical seasons start, has been defined on your workspace. Similarly, a vector meteo has already been created for you with the meteorological beginnings of the season. Instructions. Use as.date to convert the astro vector to a vector containing date objects. You will need the percent %d, percent %b, and percent %y symbols to specify the format. Store the resulting vector as astro underscore dates. Use as.date to convert the media vector to a vector with date objects. This time you will need these symbols, yeah? And make sure that you know the use of lower or uppercase. For the format argument, store the resulting vector as meteo underscore dates. With a combination of max, abs, and minus, calculate the maximum absolute difference between the astronomical and the meteorological beginnings of the season. That is astro underscore dates and meteo underscore dates. Simply print this maximum difference to the console output. All right. So first thing we want to do is convert astro to vector of date objects, assign it to astro dates. Okay, so the variable is going to be astro underscore dates. We want to assign something to that. What we want to assign is as.date, astro format equals percent %d, percent %b, percent convert meteo to vector of date objects and assign this to meteo dates. So meteo underscore dates is our variable. We're going to assign something to that. What we're going to assign is as.date meteo. Our format is going to be this. We're going to go percent %b, percent %d, and percent %y. And then finally calculate the maximum absolute difference between astro dates and meteo dates. And we'll assign this to maximum absolute difference. It's the variable. And what we want to assign to that is max abs astro underscore dates minus meteo underscore dates. And make sure our syntax is good. To open, to close. And then let's see, it wants us to print. So we'll just print it. And let's submit the answer. Impressive. Great job on finishing this course. So awesome. That completes our tutorial on Intermediate R Chapter 5 on utilities. This also completes the lesson overall on Intermediate R.